The next topic that we'll talk upon is the time series modeling. And this is yet another topic that belongs to the field of machine learning and the supervised machine learning. So, this is a slightly different domain that we are going to discuss because it's different from the regression and the classification problems that we try to solve in the industry. So where in case of the regression or the classification kind of problems, we work upon label data. This is some area where we will still be working upon the label data, but we will be working upon a data where the y variable is the most important variable here, along with the date and the time component that we have. So we will not be working upon the x variables here, even though the data file could consist of the x variables. What we'll focus upon is only the y variable and the date and time component, because we are going to work upon time series forecasting. And forecasting is a term that is used when we are wanting to predict the future values as such. And when it comes to forecasting, it is slightly different from prediction. So all the things that we do in case of regression and classification kind of problems is where we do predictions, where we try to predict the values for the y variable on the basis of the x variables that have been given to us. But in case of time series modeling, where we will be doing time series forecasting, the concept is slightly different, because we will try to predict the y values on the basis of the previous y values. Okay, we will not be able to have any x values for the upcoming future, right? For example, if I have been given a weather related data and I have been asked to forecast the weather for the upcoming 2 weeks, the upcoming 2 weeks values I can predict, but I do not know what would be the humidity level or the precipitation level, or how cloudy it would be or how windy it could be in those set of days, right? I don't have the X values known to me for the upcoming 2 weeks. So I can't call it a prediction problem, but rather it is a forecasting problem, where on the basis of the previous temperatures that were recorded, I'll let the model learn and interpret that pattern, and I'll allow it to forecast the values into the future. And that is the reason this is a separate category and not typically under the regression, because ideally the y variables that you will be working upon in this case is also going to be continuous in nature. Okay, so it will still be similar to regression, because there also we have the y which will be continuous in nature. But the difference that I want you to understand and be able to relate to is that in case of regression, we make use of a term called as correlation, because we are trying to kind of measure the relationship between the variables. On the basis of the x variables, we are trying to predict the y. Whereas in case of time series, we work on the concept called as autocorrelation, because we are going to find out the relationship between the observations here. So let's say today's stock price is dependent on yesterday's stock price, yesterday's stock price is dependent on day before yesterday's stock price, and so on and so forth. So there is a relationship between the observations of that same variable and not dependent on the rest of the variables. So that is the reason it is not regression, rather it is time series modeling that we will be applying here, where there is a relationship between the observations that we need to interpret. So that's something that I wanted to help you understand, in order to relate to the difference between the regression versus the time series domain. And when it comes to the time series modeling, let me tell you that there are two parts to it, as in two techniques that we would work upon, where one is the time series analysis and the second one is the time series forecasting. So you can also consider it as a two-step process, where the time series analysis is more towards analyzing the historical data that has been given to you, in order to interpret that over the period of time, what are the trends and the patterns that you observe, what was the kind of scenario that you have seen for the past 5 years. Based on that, what all things can you analyze and infer? All of those things are related to time series analysis, and this is more related to the descriptive analytics side, because you are just looking at the data and you are deriving some meaningful insights out of it, right? But when it comes to time series forecasting, this is where we will be building the predictive model. So, on the basis of the previous Y values that have been given to us, we will try to learn through those values, understand the trends and patterns, and based on that, we will try to forecast the future Y values. So, that is where the term forecasting comes, where you apply those predictive models as such. And when you perform both the parts out of it, that is, you firstly analyze the data, and then after analyzing it, you try to use it in order to build a predictive model that could be able to, predict the future Y values for you. That is where the entire task that we work upon is known as time series modeling. Okay, so that is what is time series modeling, and all your time series modeling related problems are those common things that we usually observe into various domains, like the stock price prediction, where we are going to predict what could be the what could be the price for the given stock for the upcoming 1 week, or based on the past 5 years trends related to the gold prices, we are trying to predict what could be the price of gold for the next 6 months. Or it could also be the company's revenue that you are trying to forecast on the basis of the past 10 years of revenue data that has been given to you. So all of these problems where you are forecasting ahead of time is where your time series modeling is applicable. And in order to implement the time series models, there are various types of algorithms that are available, where I would like to highlight, like we tried discussing in brief. um, we have the exponential smoothing as one of the family that allows us to build those predictive models which will allow you to perform time series forecasting. And within this, let me highlight that there are three different models, where the first one is the simple exponential smoothing, which is like the first order exponential smoothing. And this is where you try to consider the weighted average of all the data points that have been given to you, and the statistical technique of exponential smoothing is applied here, which will assign weights to all of the data points, where the older data points will be assigned comparatively lower weights, and the recent data points will be allocated comparatively higher weights, such that when the model is focusing upon doing the predictions are more similar to the recent values and comparatively less similar to the older values, because we know that a lot of scenarios are such where the older data does not matter quite a lot. For example, if we are talking about a company's revenue that has been given to us right from the time that the company started up, you will see that the initial sales or the revenue that the company was doing was comparatively lesser. But now if you see, the company has progressed, and you will see that it is earning quite a high revenue compared to the very initial time. So while I try to forecast the revenue for the upcoming year, my focus should majorly be on the past 2 years of data maybe, and comparatively lesser focus onto the very older data, because I am at a good position now and I just want to keep growing from here, right? So that kind of logic is what the simple exponential smoothing uses, where we give lesser weightage to the older values and more weightage to the recent values, such that the predicted or the forecasted values are more like the recent values. So that's where the simple exponential smoothing is used. However, with the help of simple exponential smoothing, you are not able to capture the trend and seasonal components that are usually present in the time series data. So just to tell you what is trend and seasonality in the data, trend is a kind of increasing or decreasing pattern that we observe in the data over a longer period of time. So the company's revenue over the period of years has increased. That is a kind of positive trend that we have. Whereas a particular stock price has constantly been dipping over the period of years. So that is where a negative trend line is what you will be able to see. So trend is one of the component which, the simple exponential smoothing is not able to interpret well in the data. At the same time, seasonality is another important component as part of the time series category, where seasonality is a common or a repetitive pattern that we observe over a shorter period of time. So let's say it could be a weekly pattern or a monthly pattern that keeps repeating, or it could be a yearly pattern that keeps repeating itself after every year. So when you observe those kind of seasonal trends in the data, like the sales going to a peak in certain months and taking a dip in certain months, that is a kind of pattern that could be observed on a year on year basis. So that is another component that the simple exponential smoothing model was unable to handle. So when we used to generate the uh, predicted or the forecasted values with the help of simple exponential smoothing, we used to get a single value, and we had to assume that the same value will repeat for a certain number of intervals, right? Of course, that was not going to suit most of the situations very well, and that is where they decided to come up with another set of models, where they created something called as Halt's linear trend model, which is a model that is also known as the double exponential smoothing or the second order exponential smoothing. This was a model created by Holt, and he was a statistician professor, and he created this model with the intention of handling the trend component in the data. So this model was capable of understanding what is the trend that has been observed in the past few years, and similar to that would be the trend that it would bring into the forecasted values. Now, this model again was useful, but wherever there was seasonality also present in the data, it could not capture that seasonality, because, as the name suggests, it would give you a linear trend line into the data. So, it would always be a straight line, no, fluctuations in that line that you would get, given that it could not handle or deal with the seasonal component. So in order to deal with the seasonality component in the data, there was Winter, who was Halt's student. They both together worked upon a model which is also known as the Holt-Winter model. These professor and the learner created this Holt-Winter model, which was capable of handling both the trend as well as the seasonality into the data. And this is the model that became quite suitable for a lot of data sets, because many a times you do observe the seasonal component present across the datas. So Holt-Winter will not only understand the trend component in the data, but will also understand the ups and downs that were seen into the older values, and will be able to replicate a similar kind of pattern when you are forecasting for the upcoming year or so. So that is one of the major or the also known as the exponential smoothing model, or the third order exponential smoothing model that we have under this family of exponential smoothing models. And apart from this, there is also another major family known as the ARIMA family, wherein ARIMA stands for autoregressive integrated moving average models, where the ARIMA in itself is a combination of multiple models. AR over here stands for your autoregressive model, and MA over here stands for your moving average model, And these two models together, when you combine, will give you the ARMA model. Okay, so this is nothing but a combination of AR plus the MA model. You also have the I part here, which stands for the integrated, which is not really a model, but it allows you to handle one assumption that the ARIMA model is based upon, which is related to the assumption of equal constant variance and mean across the data. So that is an assumption check that we need to do when we are working upon the ARIMA model as such. So that is where the I becomes an integrated part of that model. So if you are now combining the AR plus the I and plus the MA, that is where you end up getting the ARIMA model. And this ARIMA model is capable of handling the trend component in the data. It can't really handle the seasonal component in the data. So we have another model known as the SARIMA model, which is used in order to handle the seasonal component also that is present into the data. So it is also an ARIMA model, but it can deal with the seasonal component as well. So these are some of the important models that make up the ARIMA family. These models are also used to do the forecasting. But having said that, you will usually find that AR and MA alone are not so very capable of doing the forecasting very well for us, and that is where the ARIMA comes into the picture, which although it has that assumption of stationarity which I mentioned about, that the data should have that constant mean and variance, but uh, if that assumption is being handled, the ARIMA family does give you a good model with respect to the trend component. And as we spoke about the seasonal ARIMA, wherever you have a seasonality component present in the data, you don't even need to try out the rest of the ones. You can directly implement the SARIMA, and you should be able to see those spikes and throws in the data being handled well with the help of the SARIMA model. So these are a few of the important, families of algorithms that you will find, are being used in the industry in order to perform the time series modeling. And let me tell you one more important thing, that time series modeling is slightly a different domain, as I mentioned some time back, right? Different from your normal regression or the classification kind of problems. So, one of the things that I would like to highlight is the pre-processing part that happens in a normal regression classification kind of problem, and uh, or is, let's say that it's different from what we have in case of the time series modeling. So the pre-processing related steps in case of time series modeling involve some different setup, like you need to have single dimensional data, because as we discussed, even though we have the entire data given to us, we will be choosing only the y, which is the single dimensional data, and of course the date and time component, which could become your indexing column. But you'll also need to satisfy some other properties of time series data, like you should have a data which is sorted in the chronological order, such that it is able to understand the data properly. Yeah, there could be some repetitive dates present in the data. You may have to group together the data points based on that date variable, such that every date is represented by a unique value only. Apart from that, you may also require to have equally spaced time intervals in the data. So if I say that I have a daily basis data, I need to have 365 entries for the entire year. Okay, if at all the in between data is missing, I will either have to fill it up by creating those fresh records, or I may have to perform resampling, which will allow us to work upon resampling the data at an upper level. So let's say if it's a daily basis data, I may resample it to the weekly basis, or if I have weekly data, and the data for certain weeks are missing, I would like to resample it at a monthly level, and so on and so forth. So one level above is what you can take the data at, and then you will probably have the equally spaced time intervals, and the model will be able to learn onto it. So handling these kind of challenges that are present in the data are very, very important before we go ahead and build any kind of model onto it, be it the exponential smoothing model or be it the ARIMA model. So these are certain things that you should be remembering about the time series modeling. Although the y is continuous, we work upon autocorrelation here. So we will be trying to identify the relationship between the observations and not the variables, and that is how this domain is different from the regression related domain. So just to conclude off, imagine that same example related to weather that we spoke about. So if we were given a problem statement where we were given the weather related data, and based on the weather conditions provided to us, we were supposed to predict the temperature for the day. That is where a regression algorithm would have been suitable, right? Because we would predict the temperature on the basis of various X variables given to us, like the humidity level, the precipitation level, how cloudy it is, or how sunny it is. And in case of time series modeling, again, it could be a similar data that has been given to us, but what we will do is, on the basis of the previous temperature values that were recorded, we would try to predict what could be the upcoming temperature values. So this is the major difference between the regression and the time series modeling.